The speed of light in a vacuum is 299,792,458 meters per second, approximately 186,282 miles per second. At this velocity, you could circle the Earth 7.5 times in 1 second. This number represents far more than just an impressive speed. It defines the absolute maximum rate at which anything in the universe can travel, and more importantly, it represents the fundamental structure that holds reality together. When physicists state that nothing can travel faster than light, they are not describing a limitation of engineering or technology. They are describing a boundary woven into the fabric of space-time itself, one that protects the universe from logical contradictions that would make existence impossible. The journey to understanding this cosmic speed limit begins in 1905, or when Albert Einstein published his theory of special relativity. Before Einstein, physicists assumed that time flowed at the same rate for everyone, everywhere, regardless of their motion. Space was space, time was time, and the two existed independently. Motion was simply a matter of changing your position through space over intervals of time. There seemed to be no reason why speeds could not increase indefinitely, given enough force and energy. A cannonball traveled faster than an arrow, which traveled faster than a thrown stone. Why should there be any ultimate limit? The problem emerged when scientists began studying light with increasing precision. Light behaves strangely compared to other moving objects. If you chase after a thrown ball at half its speed, and the ball appears to move away from you at only half its original speed relative to your position, this makes intuitive sense based on our everyday experience. However, light refused to follow these rules. Whether you stood still or moved toward or away from a light source at any speed, light always appeared to travel at exactly the same velocity relative to you. This observation seemed impossible under the classical understanding of motion, yet experiments confirmed it repeatedly. Einstein recognized that this constant speed of light was not an anomaly to be explained away, but a fundamental feature of reality that required rethinking our concepts of space and time themselves. He proposed that the speed of light is the same for all observers, regardless of their motion relative to the light source or to each other. That this single postulate had profound implications. If light speed is constant for everyone, then space and time themselves must be flexible. What one observer measures as a meter, another observer in motion might measure differently. What one observer experiences as a second, another might experience as more or less time. From this foundation, Einstein derived that, as an object accelerates and approaches the speed of light, time begins to slow down for that object relative to stationary observers. This effect, called time dilation, is not an illusion or a trick of perception. It is a real physical phenomenon that has been measured and confirmed countless times. Atomic clocks flown on airplanes run slower than identical clocks left on the ground by precisely the amount predicted by relativity. Particles, called muons, and created when cosmic rays strike the upper atmosphere, should decay long before reaching the Earth's surface based on their brief lifetimes. Yet they arrive in abundance because their high speeds cause time dilation, extending their lifetimes from our perspective. GPS satellites must account for time dilation to function accurately. These satellites orbit Earth at approximately 14,000 kilometers per hour, causing their onboard atomic clocks to tick 7 microseconds slower per day than clocks on the ground due to their velocity. Without correcting for this effect, GPS calculations would accumulate errors of several kilometers each day, rendering the system useless for navigation. This is not a theoretical curiosity. It is applied physics that demonstrates time dilation as an everyday reality affecting modern technology. As objects approach light speed, another strange effect occurs. Not only does time slow down, but lengths contract in the direction of motion. Space itself compresses. A spacecraft traveling at 99% the speed of light would measure distances to its destination as significantly shorter than observers at rest would measure. Again, this is not a measurement error or an optical illusion. Space actually contracts for the moving object. These two effects, time dilation and length contraction, work together as space-time adjusts itself to maintain the constancy of light speed for all observers. The energy required to accelerate an object also increases as it approaches light speed, and not in a linear fashion. As velocity increases, the object's relativistic mass increases, requiring ever greater amounts of energy to produce smaller increases in speed. To accelerate an object to 99%, the speed of light requires approximately 700 million times the energy needed to send the Apollo astronauts to the Moon, and that calculation does not even account for the relativistic mass increase. When factoring in special relativity, the actual energy requirement balloons to at least 10 billion times the Apollo mission's energy expenditure. At light speed itself, the energy required becomes infinite, not merely very large, but mathematically unbounded, and therefore physically impossible for any object with mass. For a photon of light, which has no rest mass, traveling at light speed is its natural state. Photons do not experience the passage of time at all. From a photon's perspective, if such a thing could be said to exist, the moment of its emission and the moment of its absorption occur simultaneously, regardless of whether it travels across a room or across the universe. This is why only massless particles can travel at light speed, and why anything with mass cannot reach it. This leads us to a critical understanding. The speed of light is not just about speed. It is about causality itself, about the relationship between cause and effect that allows the universe to make sense. In relativity, events are described in terms of space-time, where time is treated as a dimension similar to the three spatial dimensions. The speed of light defines what is called the light cone, a geometric structure that determines which events can influence which other events. Events inside your past light cone are events that could have influenced you, because light or any slower signal from those events has had time to reach you. Events in your future light cone are events you could potentially influence, because light or slower signals from your current position could reach them. Events outside your light cone are causally disconnected from you. They cannot affect you, and you cannot affect them, at least not yet. This structure preserves causality. Cause always precedes effect within any given reference frame, because information cannot travel faster than light. However, if something could travel faster than light, it would be able to connect events outside each other's light cones. And here is where the fundamental problem emerges. Special relativity tells us that different observers moving relative to one another can disagree about whether two events happen simultaneously. For events within each other's light cones, all observers agree on the causal order on which event happened first. But for events outside each other's light cones, for events that are spatially separated such that light could not travel between them, different observers in relative motion can disagree about their time ordering. If you could send a signal faster than light between such events, you create a situation where some observers would see the signal arrive before it was sent. This is not a matter of perspective or interpretation. It is a mathematical consequence of how space-time works under special relativity. The Lorentz transformation equations and which describe how different observers relate their measurements of space and time, produce results where superluminal signals can arrive before their transmission in some reference frames. Consider a practical example. Suppose you send a faster-than-light message to a star system 10 light-years away, and the message travels instantaneously from your perspective. To you, the message leaves Earth now and arrives at the destination now. However, to an observer moving at high speed relative to Earth, perhaps traveling at 80% the speed of light away from that star system, the order of events appears different. Due to the relativity of simultaneity, this observer sees the message arrive before you sent it. Now imagine that star system immediately sends a faster-than-light reply, are also instantaneous from the star system's perspective. In certain configurations of relative motion, that reply can arrive back on Earth before your original message was sent. You would receive an answer to a question you have not asked yet. This scenario is not science fiction speculation. It emerges naturally from the mathematics of special relativity when faster-than-light travel is permitted. It is called a causality violation, and it represents a closed time-like curve, essentially a time loop. Once such loops exist, paradoxes become inevitable. You could use the reply to decide not to send the original message. But if you do not send the message, there is no reply. And if there is no reply, you have no reason not to send the message, so you send it after all. The universe becomes trapped in a logical contradiction with no possible resolution. Modern physics has no mechanism to resolve such paradoxes. There is no cosmic editor that steps in to prevent contradictions. The laws of physics are built on the assumption that causes precede effects, that the past is fixed and the future is open, that initial conditions determine subsequent states. Remove this assumption and you cannot make predictions. You cannot trace chains of causation. Science itself stops working because the foundation on which it stands collapses. Some physicists have proposed the idea of chronology protection, suggesting that the universe might possess some unknown mechanism that prevents time travel paradoxes from forming. Stephen Hawking famously suggested a chronology protection conjecture. I'm proposing that the laws of physics do not allow closed time-like curves to exist. However, this is not a solution so much as a statement of the problem. We observe that the universe enforces causality, and one way it does this is by enforcing the speed of light as a universal limit. Even in quantum mechanics, where strange phenomena like entanglement occur, information still cannot travel faster than light in any usable way. When two particles are quantum entangled, measuring one particle instantaneously affects the state of the other, regardless of distance. This seems like faster-than-light communication, but it is not. The outcomes of quantum measurements are probabilistic and random. You cannot use entanglement to send a message because you cannot control what result your measurement produces. The receiving party sees only random noise unless you send them classical information about your measurement results through normal slower-than-light channels. The quantum connection is real, but it cannot be exploited to transmit information superluminally. Nature allows quantum strangeness, but still protects causality. Given these fundamental obstacles, imaginative minds have searched for potential loopholes. If nothing can move faster than light through space, perhaps the solution is to manipulate space itself. This is the concept behind the warp drive, proposed by physicist Miguel Alcubierre in 1994. The Alcubierre warp drive would not move a spacecraft faster than light through space. Instead, it would compress space in front of the spacecraft and expand space behind it, creating a bubble of warped space-time that carries the ship along. Within the bubble, the ship remains at rest relative to local space. The bubble itself moves through the surrounding space, And because space itself is moving rather than the ship, the construction does not violate special relativity's prohibition on faster-than-light travel. On paper, general relativity permits such solutions. Einstein's field equations that describe gravity and the curvature of space-time can accommodate a warp drive metric. However, physical permissibility requires more than mathematical solutions. To create the necessary space-time curvature, the warp drive would require what physicists call exotic matter or negative energy. Ordinary matter and energy have positive energy density and positive pressure. Negative energy would have properties opposite to everything observed in nature. It would have negative energy density and would generate repulsive rather than attractive gravitational effects. Quantum field theory does allow for negative energy to exist under very specific and constrained circumstances. The Casimir effect, for instance, produces a tiny amount of negative energy between two parallel metal plates in a vacuum due to quantum fluctuations. However, these quantum effects produce minuscule amounts of negative energy over extremely small scales. The amount of negative energy required to create a stable warp bubble capable of transporting a spacecraft is astronomical, far beyond anything quantum mechanics appears to permit. Some estimates suggest you would need negative energy equivalent to the mass of Jupiter or larger, and it concentrated and stabilized around your spacecraft. No known physics allows for this. Furthermore, detailed analysis of warp drive solutions reveals additional problems. Many versions are unstable, meaning small perturbations would cause them to collapse. Others require infinite amounts of energy to initiate or maintain. Some cannot be turned on or off without violating causality, because creating the warp bubble would require sending signals faster than light. Perhaps most importantly, many warp drive configurations would allow for time travel. If two warp bubbles pass each other going in opposite directions, or if a warp bubble is used to travel in a path that returns to its starting point, it can create closed time-like curves, bringing us back to the same paradoxes that faster-than-light travel creates. And the warp drive does not actually escape the restrictions imposed by relativity. It runs into the same fundamental barriers that prevent faster-than-light travel, merely approaching them from a different angle. The apparent loophole closes upon closer examination. Another proposed shortcut involves wormholes, hypothetical tunnels through space-time that connect two distant regions. Instead of traveling across the vast distance between 2 points, you would enter one mouth of a wormhole and emerge from the other mouth, potentially light years away, having traversed only a short distance through the wormhole's throat. General relativity does permit wormhole solutions. The mathematics allows for these space-time tunnels to exist as valid solutions to Einstein's equations. However, natural wormholes, if they formed at all, would be microscopic, are far smaller than an atom, and would collapse almost instantly. Gravity would pinch them shut in a tiny fraction of a second, faster than light itself could pass through. To hold a wormhole open long enough for anything to traverse it, you once again need exotic matter with negative energy density. The throat of the wormhole must be threaded with negative energy to counteract gravity's tendency to collapse it. As with the warp drive, the amounts required are enormous and far beyond what quantum mechanics seems able to provide. Even if you could stabilize a traversable wormhole, it would almost certainly become a time machine. If you took one mouth of a wormhole and accelerated it to high speed, time dilation would cause less time to pass at that mouth relative to the stationary mouth. An observer could enter one mouth and emerge from the other at an earlier time, traveling backwards in time and creating all the paradoxes associated with time travel. Some physicists speculate that quantum effects would destabilize any wormhole the moment it threatened to permit closed time-like curves. Others argue that the universe's rules might prevent traversable wormholes from forming in the first place. Either way, wormholes offer no clear path around the fundamental constraints of causality. A pattern emerges when we examine all these proposals for faster-than-light travel. Whether through direct acceleration, warping space, or tunneling through it, every method encounters the same obstacles rooted in the structure of space-time and the requirement for causal consistency. And the universe appears deeply committed to preserving causal order, to maintaining a clear distinction between past and future, between cause and effect. Light speed is not an arbitrary barrier. It is the speed at which causality propagates, the maximum rate at which information and influence can spread through the universe. This cosmic speed limit has profound implications for space exploration. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. Even traveling at the speed of light, which is impossible for any material object, would require more than 4 years to reach it. At more realistic speeds, say 10% of light speed, which would itself require extraordinary technological advances, the journey would take over 40 years. The nearest star known to have planets is farther away. The galaxy is about 100,000 light-years across. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years distant. These distances are not merely inconvenient. They represent fundamental limitations on how quickly we can explore or communicate across cosmic scales. Science fiction often depicts starships crossing the galaxy in weeks or months, with crew members experiencing space travel as routine. The reality is starkly different. Interstellar travel, if it ever becomes possible, would require generation ships where multiple lifetimes pass during the journey, or some form of suspended animation or near light-speed travel, where time dilation allows crew members to experience the journey as shorter even as centuries pass on Earth. Neil deGrasse Tyson has pointed out that the energy requirements alone make faster-than-light travel seem like wishful thinking rather than plausible engineering. To accelerate even a small spacecraft to 99% of light speed would require energy resources equivalent to thousands of nuclear power plants running for decades. The infrastructure to generate, store, and apply such energies does not exist and may never exist. And even at that tremendous speed, still not quite light speed, a round trip to a moderately distant star system would see everyone on Earth age by decades, while the crew ages only a few years due to time dilation. Beyond energy and engineering challenges lies the deeper issue of physics itself. The universe is not required to be convenient for our ambitions. It operates according to laws that prioritize consistency over human desires for rapid space travel. The speed of light limit exists because space-time must maintain its structure, because causality must be preserved, because the universe must remain logically coherent. Some have suggested that future discoveries might reveal ways to bypass these limitations, that our current understanding might be incomplete, and that new physics could permit faster-than-light travel after all. This is possible in principle, though increasingly unlikely as our theories become more thoroughly tested. Special relativity is not a tentative hypothesis. It is one of the most precisely verified theories in all of science, confirmed by countless experiments across more than a century. GPS satellites, particle accelerators, cosmic ray observations, and precision atomic clock measurements all validate its predictions to extraordinary accuracy. Any new physics that permits faster-than-light travel would have to explain why all of our current observations align so perfectly with relativity's prohibitions. General relativity is similarly well tested in its domain. Gravitational time dilation, the bending of light by massive objects, the precession of Mercury's orbit, gravitational waves from merging black holes. All these observations match Einstein's century-old theory with remarkable precision. A theory that allowed warp drives or stable wormholes while still explaining all the phenomena general relativity correctly predicts would need to be extraordinarily sophisticated and would need to explain why we see no evidence of these exotic space-time structures anywhere in the observable universe. The universe appears to value consistency above all else. Physical laws are the same everywhere and at all times. Cause precedes effect. Information cannot propagate faster than light. These are not arbitrary restrictions, but fundamental features that allow reality to function in a coherent manner. Faster than light travel pulls too hard on too many of these supporting structures. It destabilizes causality, creates logical paradoxes, and threatens the foundations on which physics rests. And this does not make the universe hostile to exploration or discovery. It simply means the universe operates according to principles that may not align with our intuitive expectations or fictional narratives. The distances between stars are vast, precisely because that vastness has meaning in a universe where cause and effect must be preserved across space and time. Rapid galactic travel may remain forever beyond reach, not because we lack sufficient cleverness or technology, but because the universe is structured in a way that forbids it. Understanding these limitations invites us to appreciate the universe on its own terms, rather than demanding it conform to our preferences. The speed of light defines the rate at which change propagates, at which information flows, at which the future emerges from the past. It ties together space and time into a unified whole, establishes the relationship between energy and mass through Einstein's famous equation E equals mc squared, and draws the boundary between causally connected events and those that remain independent. There is elegance in these restrictions. The same principles that prevent faster-than-light travel also ensure that the universe behaves predictably, that experiments produce consistent results, that mathematical descriptions of nature work reliably. Science itself depends on causal order. If effects could precede their causes, experimentation would become meaningless because we could not establish which variables influenced the which outcomes. The prohibition on faster-than-light travel, frustrating as it may seem for our dreams of galactic civilization, is ultimately what makes the universe comprehensible. It is what allows science to function, predictions to hold, and reality to maintain coherence. The speed of light is not just a maximum velocity for material objects. It is the foundational constant that structures how reality itself operates, ensuring that space and time form a stable framework within which events unfold in logical sequence. Our universe may not be designed for convenient traversal on human timescales, but it is designed, or perhaps more accurately, it has emerged as a coherent system where causes lead to effects, where the past is settled and the future is open, where information and influence spread at a finite maximum rate. Faster-than-light travel would unravel this careful structure, creating paradoxes that have no resolution and violating principles upon which all of physics depends. The boundary is absolute, not because of insufficient technology, not because we have not discovered the right trick, but because the architecture of space-time itself forbids it. Every experiment conducted, every theory formulated, every observation made points to the same conclusion. The speed of light stands as the universal constant that defines how fast change can propagate through the cosmos, and crossing that boundary means leaving the structure of reality behind. This is why faster-than-light travel remains not just impractical, but fundamentally incompatible with the universe we inhabit.